So let me introduce our last speaker for online sessions, Stefan Ohm. So he's one of the biggest experts in gamma ray astronomy, so in HESS telescopes, which we discussed yesterday and today. And actually, just a fun fact that during his leadership at the operation department, so we got a record data acquisition in HESS. But today, as the last talk for the session, he will discuss about outreach, about visualization. It's actually very interesting here because we have people from research, we have people from visualization at JetBrains, and I hope it will be a fruitful discussion, or maybe we can have some insights or common ground. Okay, Stefan, thank you, and yeah,
thanks.
Let's start.
Yeah, thanks, Dima, and thanks everybody. It's a pleasure to talk about this for the first time in a talk, actually. I had a short post at the ICRC 2 years ago, but I wasn't able to really talk about the science communication work I've been doing in the past 2 or 3 years. So I hope you can see my screen. I wanted to just give you a very brief introduction to what we have been doing, and then show you 3 examples that we did. So cooperations with the Science Communication Lab, which is based in Kiel. And they are experts in artistic realizations of data-intensive things. So it's not just astrophysics, they also do health and bioengineering, but also work for industry partners. So in astroparticle physics, when we talk about the non-thermal universe and its messengers, we basically communicate on 3 levels. So us physicists and astronomers, we of course interested in the sources itself. What's the physics of the sources? The supernova remnants, for instance, here on the left-hand side, how do they work? How do they accelerate particles? Or others are interested in much larger scales, galaxy clusters. Are they particle accelerators? Where does the gas come from? Whatever. So this is what interests us. And often when we communicate our science results, we focus on the sources. But this is only one aspect, because if you communicate astroparticle physics results, you also have to talk about how we get the information. And this is basically through the messengers we are using. And the 3rd level is a much more practical one. How do we actually detect these messengers? And so I wanted to give you just these three levels and maybe keep them in mind when we go through the talk. So when we talk, so if we think about gamma rays and the sources we detect in very high energies, you see a plethora of different source types, of different types, of different origins of the emission. You're looking at very different physical scales. You're looking at very different temporal scales. So you have sometimes binary stellar systems that change their behavior on months to year timescales. You have supernova remnants, thousands of years. Or you see entire galaxies, and there you're talking about millions of years. So you somehow have to convey a sense for time scales and for physical scales. In the night sky in TD gamma rays looks like this. So we do have a pretty similar picture to the thermal blood sky at lower energies. We have many different sources, and we know from shorter wavelengths, in many cases, what they are, or we at least suspect what they are. So one thing we want to communicate, except for the sources, is our cosmic messengers. And when we talk about astroparticle physics, let's leave gravitational waves aside for now. Then we're talking about cosmic rays, which have been established more than 100 years ago, which reach the highest energies. They are easy to detect, but they are electrically charged and hence are deflected in cosmic magnetic fields. And they are also easy to destroy on their way to Earth. So if you're aiming at communicating what cosmic rays are doing and where they are coming from, you have sooner or later address these properties. For gamma rays, it's a different story. They are very numerous, they are not deflected, so they are very easy to detect. On the downside, they could be annihilated in the accelerator if you have, for instance, very strong radiation fields. Or they are very easy to destroy on their way to Earth. So the horizon or the distance we can see gamma rays at a certain energy is rather limited. So you also have to convey this message. And then the elusive neutrinos are, of course, very new. So it's sometimes a bit harder to talk about neutrinos in public, actually, because their pro is that they almost have no interaction with matter whatsoever. So they can easily escape the accelerator and tell you sometimes the most about cosmic particle accelerators. And they're also not deflected. So they also go in straight lines to the observer. But the pro is also a con, because since they almost have no interaction with matter, they're also very hard to detect. So when we talk about these messengers, we somehow want to convey how they are produced, how they propagate through space, how they interact, and how, for instance, cosmic rays produce gamma rays in interactions. So how do we measure gamma rays? And this is the link now to the telescopes in the way we measure photons, for instance, here in this example. So we have Cherenkov telescopes that use the atmosphere as part of the detector. So this is one ingredient, one info you want to convey. You collect Cherenkov light emitted by the charged particles in the shower, often via an optical reflector that you put in the light pool. And then this optical reflector reflects the light on an ultra-fast camera. So this is the main principle of gamma ray telescope, a ground-based one. And this is also something that you would want to convey as information if you talk about science results and how we measure, for instance, gamma rays. Of course, this is different for all the different messengers. So for neutrinos, you would display, for instance, the Ice Cube Observatory and explain how the Cherenkov light is produced when neutrinos interact. So let's start with the first animation. So this one is about Eta Carina. It's a binary star system. I will stop my screen and share the first animation with you. I hope this works. If it doesn't, Dima, maybe you have to show it locally. Sorry, where's... Yeah. Should I share the sound? Maybe I do not share the sound and just show you the video. I hope you can see the screen. So this is now the first animation that we produced during the Corona time. This is when, for the first time, very high energy gamma rays were discovered from Eta Carina. So this is a binary stellar system in the Carina Nebula. And in the animation, we start off with the Earth and the night sky view from Namibia, and we slowly zoom into the binary system and go back to 150, 160 years ago, when there was a massive eruption from the binary, from the primary star in the binary system, and go now into the system where we display the stars with the sizes we actually infer from real observations. So the relative sizes of the two stars are now to scale, and inspired by, for instance, measurements of the sun, we also show eruptions on the surface of the star and in the corona. So now the animation displays what we know about the orbit of the two stars. So not just the size, now it's the orbit. So these are physical orbital solutions of the stars. We also ingest the velocity of the stars, and in the animation, you actually have a very realistic movement of the stars. So you see every 5.5 years, they go one full cycle. You see that the speed of the stars increases as they get closer to each other and then decreases again. The winds now collide and they form a colliding wind region. And the location of the colliding wind region is again inspired by real physics. So we know the place where the run pressure balance happens. And this is where we actually put the shock in this animation. And these clouds are now meant to illustrate the colliding winds that then slowly move outward. At this stage, we also ingest real X-ray data. So this light curve is from long-term monitoring from the RXTE satellite. And we put it on top of the velocity in this inlay, in this 1D inlay. And the main result of this animation was, or the main result of this scientific paper was the Hess detection of gamma rays from Eta Carina. And these are actually the small data points that we now also overlay on top of the X-ray light curve. So you see that the animation has a lot of stuff going on. So you have text inlays, you have description, you have graphics inlays, you have a coordinate system and a grid. So there's a lot of stuff going on, and I will talk about this in a minute. We then also changed the perspective and went into the shock cap and into the colliding wind region to also show how the properties of the different winds could be visualized. Okay, so this one is actually a pretty long animation if you compare to others. So this one is now almost 4 minutes, 3.5 minutes, and was, as I said, the first of this kind. Let me change back. Good. So you should see the slides again. So just to recap what you've just seen. So the idea was to be as close to reality as possible while visually appealing. And that meant that we could ingest for this very good and well-known system physical parameters of this, first of all, of the stellar eruption that happened 160 years ago, and that formed the homunculus nebula. So you see a comparison between the real Hubble NASA image on the left bottom side, and then how this looks like in the SciComm Lab animation. But we could also ingest the stellar parameters and hence model the winds that were colliding. The movement of the stars was another ingredient that was inspired by physics. But we had to sacrifice on the colliding wind region itself. So this is actually pretty hard to visualize since you want to have a colliding wind region, but then it can't be opaque. So it has to be transparent and somehow still apparent to the viewer. So this was a bit of a struggle. The other thing is that if you go to the YouTube animation, there is also a soundtrack. So we cooperated with electronic artist Alba Noto on this, and this was actually pretty exciting. The entire animation took about 4 to 5 months in preparation, discussions, and it was actually quite a bit of work. Also, we had to find a common language, actually. This took not as long for the next one. So I will show you now the GRB animation. This one here, you see, is much shorter. So we try to convey less information or the essence of the information in a shorter video, because 3.5 minutes is actually pretty long and many people don't really watch through. So here we have the GRB 1908-29A, the one that was first discovered in TV gamma rays with the Hess telescopes, where we show and are inspired by how a jet forms when a massive stellar object, so a massive star, collapses, produces a supernova explosion that is left behind, and then the jet of material plows through the medium. In this case, it's not just the explosion that we show, but also the jet itself and how we visualize it. Also here we had to compromise because the animation engine required us to constantly inject energy, whereas in reality we had one single explosion and then the jet moving through the ISM. This is now indicative of an electron that is deflected in magnetic fields and is emitting synchrotron radiation, and this is this beam here in the center that is now emerging. Coming to the detection, this is actually a real model of the Swift satellite. So you can get models of the Swift satellite or from telescopes in CAD format, and then you can actually feed that into your animation software. And in this case, we also show that the emission was detected with HESS over 3 days. So we had the proper movement of telescopes. We had the parking of the telescopes during the day. We had a proper geographic model of the Earth. So what you have seen before, this was actually the real landscape of the Earth. And actually, if you look closely, it was also the landscape of South Africa. Okay, so if you look at the animation, there's also a lot going on, but there is also a lot of physics that went into the animation and tries to convey what we have actually measured. So the star itself, we can infer, so the star that exploded, we can infer from multi-wavelength observations. From the HESS measurements and X-ray measurements, we can actually infer the jet properties. So how fast does the jet move? How wide is the opening angle? And in particular, the opening angle is reflected here. So this one was about 5 degrees. We show how the jet moves through the interstellar medium and zoom into the shock region. So this is where the actual particle acceleration happens. And so in the animation, we had 2 fluids, one that was carrying the particles, and the other one was the background gas that was moving at the same speed. So this is nowadays possible and quite easily realized. And this is how we try to illustrate the gas particle coupling. And then the deflection of the electrons was also quite realistic in terms of the relativistic effects that we took into account. The same is true for the relativistic beaming that we try to visualize here. And the latest findings of the intensity profile, so the radial dependency of the intensity of a jet with respect to the main axis, is a power law with e⁻⁴ index. And this is also tried to be realized here. So you have kind of a very fine needle of emission, and then the emission falls off quite rapidly. And as I mentioned, we had a rather realistic geographic model of the Earth. And we had CAD models of the Swift Observatory and the HESS telescope. So we can actually move the telescopes in the animation. We didn't quite manage to actually project the real night sky that was observed at the time of the HESS observations into the animation. If you would have had a few more days of time, we would have actually also done that. Also in this one, we have collaborated with Albanotto, who produced the soundtrack, and this was again pretty exciting. You can tell that here we left out a couple of things. So we did not include the image-in-image graphics, no 1D information. We also did not include any text. We just used the YouTube subtitles. And so the viewer can actually decide which language they want to watch the animation on and what want subtitles. And it also gives you the flexibility to later add translations. And so we added, I don't know, a dozen different languages for this one. And we also did it for the next one I will show you in a second. Okay, the last animation is the first detection of a galactic transient in TV gamma rays, and that's Ares Ophiuchi. It's a white dwarf red giant binary system that explodes every 9 to 25 years, and in 2021 was the last time that this nova went off. And the HESS telescopes were able to observe gamma ray emission from this object for the first time up to a TeV in energy. So this was actually pretty exciting. Okay, so let me show you the last one. It will be even shorter. So it's just a bit over a minute long. Hang on. Okay, sorry. Good. So also for this one, we added sound, but this time not with the Alba Note because the time was too short for this collaboration. So here again, you see a binary system. We have a white dwarf. This is this guy here that accretes particles, that accretes matter from a companion star. This one here. You form an accretion disk, and at some point the mass of the white dwarf exceeds the Chandrasekhar mass, and a thermonuclear explosion is happening and is ignited, and this is what you can see here. So you reach the critical limit, you expel 10⁻⁴ solar masses of material, and they move predominantly towards the poles out of the out of the system. And where you see the blue filaments, these are also the regions where material is moving fastest and where we believe that the gamma ray emission is originating from. In this case, we zoom into the shock and display how the proton-proton collision works. So again, we have two gas. So we have a background gas, the interstellar medium, and we have the shock moving through, and a proton that was accelerated interacting with the gas particle, producing a pi0, which then decays into a photon. And this photon is what we then see on Earth after it traveled to us. In this case, we did not go all the way to show the path of the particle to Earth and then the detector again, because we wanted to be, well, we did not want to repeat ourselves too much. So also here you can see a couple of quite realistic physical properties that we try to get into the animation. Most importantly, it's a rather realistic treatment of the accretion process. So the way the gas is channeled into an accretion disk around the white dwarf and then accretes onto the white dwarf surface. The physical scales of the stars, the explosion itself, and also the propagation of ejecta material is also pretty accurate and is inspired by Hubble observations and very high resolution observations at other wavelengths, where you can actually see the ejecta after a couple of years in this hourglass shape. We also have an adequate depiction of the most likely origin of the highest energy gamma rays, which is at the pole regions of the ejecta, where the material is also moving the fastest. And this is where the fastest shock is, hence you reach the highest energies. And then the zoom into the shock region is also actually quite nice, and I like it very much because it illustrates how the inelastic proton-proton collision process actually occurs, how we produce then a gamma ray out of a pi0 particle. So these were now 3 different examples. And to briefly summarize before I give you a short glimpse of what comes next, we have established by now a pretty strong collaboration between SciComm Lab and DESY in astroparticle physics. SciComm Lab do a lot of work for DESY in general, so they are not just limited to astroparticle physics, they are also involved in other collaborations and cooperations. We are aiming at realism, physical realism, and conveying physics results while being visually appealing. And this is not always easy because you have to find a common language, and you of course have to sacrifice. You cannot be physically accurate always, because then you will lose the viewer. The animations itself become more realistic. So what you've seen here was were animations produced with Cinema 4D and dedicated plugins that are developed sometimes by physicists, for instance, to have Newtonian gravity included, fluid dynamics, you have turbulence. And all that goes into this Cinema 4D via plugins and is then used by the SciComm Lab developers. we are trying to communicate and to talk about more about the how, not just what we find, but how we measure. So the instruments, the data that we take, and how we process the data. And this then actually opens up quite a few possibilities. So you can talk about more about the microphysics, for instance, and you could immediately see that there is potential to go deeper. If you add more detail, you can actually use this to go to lectures, and go into schools and talk to students about the physical processes. They are very generic, they are very general, and so this is actually a really good way to visualize what the physical laws are actually. We're also looking into real event displays. So this is work in progress, so that we can actually use real events and put them into event displays. We have now also used air shower simulations, real air shower simulations, and put them into the Cinema 4D engine. And this is also an ongoing effort. As I said, in general, this opens up a lot of potential for science communication applications, all the way from very top level flashy things like the animations you have seen, up to scientific posters and much more detailed and physical content. We currently work on an interactive web-based framework to combine the different sources, the different messengers, and the detectors in a joint theme. So this is meant as a core framework that is then easy to expand and is actually modular. And I will show you a couple of, let's see if that works, a couple of first impressions. So this is what I got yesterday from our friends at SciComm Lab, 2 screencasts of the website that they are currently working, and keep the general concept in mind. So you have the sources, you have the messenger, and you have the detectors. I will just play it, and maybe we can talk about that later. Yeah, so this was the first one. On the right-hand side, you have a view of the entire galaxy. So they fed galaxy catalogs into this engine, put sources where we suspect them to be at a certain distance. And then you have this interactive window here where you can actually rotate, look into the source, zoom, and you have the illustration, you have the explanation in text form on the left-hand side. The second screencast shows you now the instrument perspective. Yeah, that was it. So these are just 2 examples. And here are a few more screenshots. So this webpage will come with 3 different modes. One is a story mode, which you probably know and have encountered on news pages, in particular during the Corona pandemic. Like in the New York Times or other major journals, where you went through an article and then interactively new information popped up, infographics, whatnot. This is this top row, which gives you a first impression of the story mode. there will be this explorative mode as in the first screencast, where you can actually go through and explore for yourself. And then there will also be a kind of a video mode that runs you through the entire thing, shows you, for instance, a tidal disruption event. And yeah, so it's a bit like the story mode, but more guided. Okay, I think I will leave it at that, and am happy to take questions.
Yeah, thanks, Stefan, very much. So it was really cool. And I have a few comments, but yeah, first maybe somebody from the audience or from remote speakers. And I also have a comment regarding GPT stuff, but maybe later. Okay, please go ahead.
Okay, I will start here. I am Vladimir. We have met about 2 years ago.
Yeah, hi.
Yeah, pleased to see you again. I had just a quick idea after taking a look at this amazing web visualization. So there is a quite new technology for like photogrammetry called NERF, based on neural networks, that like basically works. I don't know whether you are familiar with it. So you have multiple photos of some scene from different angles, and what this neural network does, it takes all these images without knowing beforehand from which exact angle they have been made, and then it reconstructs a 3D model of this territory, which is covered by these photos. So of course we can't like launch a photo drone in space and take photos there, but I think it would be an amazing idea to take such photos of like observatories that we have, like just launch the drone, make like 100 or 2 of photos just from different locations, then load it in a neural network, and then get the 3D model. And yeah, I personally would like to try this. So if there's such data available somewhere, I will be happy to collaborate personally.
Thanks. Interesting idea. And a quick anecdote. Actually, we didn't know where our CAD models of the small telescopes were, but somehow our SciComm lab guys, they had them. So I asked them, where did they get them from? And there was a guy who collects images or scrapes the internet for images of telescopes. And I don't know how he did it. I suspect it was by hand, make the CAD models out of them. Wow. And I think he used something without the neural networks, combined things into the 3D structure, and then sold them. So, wow. Yeah. So yes, we had to kind of buy our own CAD models back. But this is actually a pretty good idea, and for many observatories, you probably don't even need the drone. You already have the images available. No?
Yeah. I need to look at it.
But yeah, this is a good idea.
Any further comments, questions, or may I ask mine? I guess I already said this idea, but now since we got this language model session beforehand, and we have still speakers here connected. So with your on your last slide, when you show this screenshots from I mean how do you want to organize a layout of the site? So I guess it would be nice to have like a kind of chat bot which maybe guide you, and you can interactively actually ask some questions. For example, like what is I don't know, what's the difference between gamma ray and X-ray and so on, and then this chat GPT can actually answer you. But I guess this requires some fine tuning, right? To not to say some wrong.
we need to check. So like for some basic knowledge, it should work, but for some specific field, like we should test. But I think it should be feasible.
Yeah, I guess Oh, just go ahead, Stefan.
This is one application we use. at the moment to fill information into this, not into the story mode, but into this explorative mode. Getting the content is the hardest part. Yeah, the animation is one thing, but then you have to add the context, you have to add the information actually. And this is work. And this was done by people all the time. And now for this page, our master student is actually using ChatGPT, asks, give me a short description about what is neutrino astronomy or how does a tidal disruption event work? And then he uses this short explanation, revises it, and gets the text much faster. You still need the knowledge. So you still need to look out for obvious mistakes, but this helps in the preparation. That's for sure. A chatbot is, of course, the next level on top of that, which I think is also a very good idea.
And I guess this fine-tuning by Attila and Anastasia can be actually used for this or
yes.
not.
So we could at least reuse the data. So maybe the fine-tuning process could be a bit different, but the data itself, yeah.
But I guess you should be fast because maybe soon, yeah, we'll get some letter from ministers that one cannot use ChatGPT, yeah, for filling the websites, Stefan.
There are no guidelines yet, so it's still a bit anarchistic, and that's good. It's not harmful, so it's anyway just super boilerplate info that you can also get from any paper.
Yeah. I have also a question regarding the computing resources, because, for example, I guess the graphics in JetBrains down in Munich, yeah, right? I mean, the rendering and stuff like this.
We do it in the cloud. So like in our servers are in US actually.
So you just
yeah. Okay. So we don't have our own GPUs, but we use them like dynamically depending on the load.
Because I mean, given the energy crisis, I just wonder. So how this is gonna be rendered and so on. I mean, if or I mean, for this outage, there is no restriction to outsource this to United States. I mean, for rendering, or what is the rendering like fraction in budget? Let's say it's like significant part to render all of these things, or?
Well, so most of the time, maybe I show you another quick example.
The SciComm Lab is a private company, right? So they are not.
It's a private company, yeah. So what they do is most of the time we are working in this wireframe format. So it is actually pretty hard to visualize or get a sense of how the final product will look like, because you're looking at test particles, you're looking at lines and whatnot. The rendering is done at the very last stage. Most of the time, not more than once. So you want to get as close as possible before you go into an 8K rendering. That's clear. They have their own pretty performant desktop PC with a couple of GPUs. But that's also the bottleneck. That's expensive if you have your own. I'm not aware that they are using the cloud. The big question is, if you go more interactive, you probably need your own infrastructure. Yeah, so you have to do the rendering live. Yeah, for instance, for this website, if you either pre-process everything or you render live, and I think live is probably the way to go.
And like I think the web and YouTube versions are very different in their nature, because like Cinema 4D uses path tracing to do physically accurate lighting, and on the web we have rasterization, so it's like kind of fake, well, to make it feasible to run in real time. Yeah. So there also could be some shader stuff, so that's very interesting.
Yeah, I also had some question, but already forgot. Yeah, of course, Corsica simulation. Yeah, because we also started to do this with Unity and so on, but I mean, for different reasons, it's kind of suspended. I mean, this project. But what is the status of Corsica simulation with SciComm Lab? Because I mean, the Corsica simulations are Corsica visualization is a straightforward stuff, yeah, because we can simply get a particle list and what we need just to trace them.
Yes, and
our
I think
yeah.
It's put on hold for the moment because the focus was on this multi-messenger website, the general one. And so the particle, or so the shower simulations were not super urgent for this. It's clearly one of the extensions we plan to have. I don't know what the status is. I think Jonas fixed a couple of the remaining problems and put the event lists and the particle lists on a website, and so SciComm Lab have them. And I would assume this is a job done in a week at most, because I handed them event displays and they managed in an afternoon to put this in a nice format.
Yeah, actually, Jonas used this library we developed. We plan to use for our business. It's with Corsica 7, but yeah, unfortunately, it's kind of suspended. But yeah, it seems that we still have a chance to also to produce our simulations in time, maybe at some point.
Yes.
Yeah.
Okay. Do we have any comments in chat? I don't see any. Any comments from remote speakers? No. Then I guess we can close our online session and thank all of the speakers. It was very nice to see you, and hopefully we can continue.
Yeah, thank you very much. Thank you.
Likewise. Thanks a lot. Bye-bye.
Ciao.